I'm very happy to give a lecture at this school, which is, I think, well prepared by professors over there. Thanks so much. This is the School on Nuclear Fusion Reactions and Lattice-Confined Fusion. So I will talk on two related topics. One, nuclear fusion, nuclear reactions in metals and liquid. And the other one is just cold fusion, okay? So this is what I'm going to talk. My interest in ultra-low energy reactions in metals started with cold fusion in 1989. I'll talk about the experiments I have continued to develop since then, these things. Recently, I have been observing huge energy generation induced in metal foils by just using looking at the photon calorimetry. So I will talk after that, I will talk in these topics and summarize. The announcement of Fleischmann and Pons in 1989 came as a shock to researchers in various fields. So they had a press conference at the University of Utah. They said that nuclear fusion in a desktop electrolysis experiment, that is the heavy water electrolysis, palladium cathode and platinum anode. A large number of heat, much larger than electrolytic heat, they said dual fusion occurred in the palladium cathode. However, follow-up exams were held all over the world, but in many cases, excess heat cannot be confirmed. November in the same year, DOA panel report, current experimental and theoretical research results do not support the occurrence of cold fusion in solids. Then they said no special fund for cold fusion research. Then the cold fusion was almost rejected by various academic societies and was treated as a pathological science. However, cold fusion is not completely dismissed, but reactivated recently. Some groups, United States, Japan, Russia, China, Italy, France, and so on, continue to develop various cold fusion experiments, right? So let me think. Nuclear fusion in metal at very low temperature, is it possible? This is the diagram of the various plasma. These are the plasma experiment on Earth, and these are the plasmas in the cosmos. We know the reaction rate in plasma is written by this formula. This is proportional to the number of densities and the cross-section times velocities, average value of these. So the nuclear fusion in star, I would say these are the here, white dwarfed, solar core, brown dwarfed, and so on. These are, we can say these are the high temperature, high density plasma. For example, sun of core is something around the energy of 1.3 keV. And those makes a very much high reaction rate. Therefore, if the cross-section is higher, but everyone knows that the first step of this fusion started with a weak interaction. Therefore, the cross-section is very low. On the other hand, we know the ITER experiment here. It's a hot fusion on Earth. And I would say this is high temperature, very high temperature, but very low density plasma. And because of the plasma should be confined by magnetic field, the law is something like this. But the energy or temperature is very low, very high. And also, they are thinking to use the very high, very large cross-section reaction, like DT going to alpha N. There's a resonance, as you see the previous speakers. And then here, that's our cold fusion stuff. Cold fusion in metal. That we say it's a ultra low temperature and medium density plasma. Low, the density is very high compared to the ITER project, 10 to the 9 times. But the energy is very, very, very small. So if you calculated simply the cross-section of the, for example, DD reaction, it's the tremendous small cross-section. So the problem is how can make the uses of these reactions an energy source? Let me see. And we know the reaction cross-section, very low energies. It is written by this way. This is just a bare cross-section. And if there is some kind of environment effect in this reaction in plasma, we have some kind of enhancement factor. So therefore, the in various plasmas, this reaction cross-section can be modified. For example, if we want to get a effective potential for effective energy 450 electron volt, then the plasma fusion can be possible. So therefore, there might be screen energy enhancement, or we can produce a medium temperature plasma by, let's say, using the ultrasonic cavitation and so on. Of course, it's an unknown mechanism might be there, lattice assisted and so on. That's the things we thought in the beginning of this cold fusion process. So we started the low energy nuclear fusion in solid metals, especially for the D plus D reaction. And we see the screen potential in solid. So maybe this subject is already given by the previous speaker, and I have lots of slides to show. Maybe we can skip these things, how the screen potential is induced in the conduction electrons, C of the conduction electrons. I just showed it. This is a conduction electron C, and you put one positive charge over here. The density of the average density of the electrons is different, polarized. So you have a polarized electron density here. Then you have a screen potential. So if you take out this out, this is the induced electrostatic potential. And actually in the center of here, you got the effective energy like this. This is just a screen potential energy. The simple approximation, you can add this screen potential to the kinetic energy of the entrance channels, okay? Therefore, very much increase the cross sections of this two-body reaction. So this is our low energy beam generator. Okay, I just skip, but this just say that we use a duoplasma ion source and the neutron current up to 500 microamps. And the neutron energy is 2 to 100 keV. We have a 2 target station here. We can do the using the solid metal target over here. And then the beam bend to the vertically by 60 degree. Then we can put the liquid metal target over here. That's our apparatus. And this is how to measure the DDP reaction in solid metals. Impinged D plus beam serves the target D. So therefore, so this is just a density profile. I just take a elastic recoil detection. Here, the zero surface is over here. And then after the impinging the neutron, some of the target may show this kind of neutron density distribution. And the other one is like this and so on. So therefore, the target density has a various problem. How to estimate? Because they have a temperature dependence and host material dependence, and also long-term fluctuation. We have anyhow to overcome by developing a technique to do that. And this is the typical spectra, just a single detector measurement case, the one silicon detector. By the way, the silicon detector is put just the backward angle, and before that, there's a filter magnet because we are using the beam decelerating beams. Therefore, the neutral beam can go through. So therefore, without this magnet, we must see the reaction with the neutral beam. Just reject for that. So anyhow, we can do it, and sometimes we are using the delta E counter telescopes. For example, this case 50 to 150 silicon detectors. Right? So this is typical result of our measurement. So this is the tick target yield. We normalize all the yield at the 10 keV here, and down measure the yield, relative yield down to here. And here you see if there's a no screening potential, this goes down this way. Here you see the enhancement. Enhancement factor is just like this. I just to get the screening potential, for example, in this case, we try to reproduce this behavior by changing this 600 screening potential value, because the fixed target yield is given by this formula. We just change this one and get a best fit to the data. So this is the screening energy obtained in this measurement. It's a very long time ago, though. And this is the compiled data in 2006. That time, these are the red result in the Rolf's groups and Chelsky's group and so on. But the huge value of screening potentials, because we can estimate the conduction screening potential from conduction electrons, so-called Thomas Fermi screen. That's just like this order, or for the Fermi energy is 5 electron volt case. So maybe the less than 100 electron volt screen energy, that's normal things. But beyond that, very large screen potential we see. And then we want to know the effect of positive ions. So this is the picture. Just show the picture what the case is. Just plasma, because in this case, plus and minus charges are in plasma. So therefore, if put a target Z here, then the minus charge attractive to this central charge Z, but positive charge get away from the kick out from this region. So therefore, you have a low density, polarized charges like this. This is a density, average density, and the ion density is going down close to this point, but the electron density is going up like this. So therefore, there's two screening potentials from electrons and ions, simply estimated by Thomas Fermi, and also the divide Heckel approximation. And the total screening length can be described this way. But for the electrons, there's a quantum particles. Conduction electron is quantum particles. Therefore, the string length is described by this formula. But for the classical ions, it's a classical particle. So it is just depend on the temperature, like this. What is a good test? So lithium liquid metal is a very nice place, a laboratory for dense plasma experiment, because we have an ion electron system. In the solid case, only the electronic screening, because no polarized electrons. But oh yeah, there's a polarized electron, only polarized electrons, but no no ion polarization. But above the melting point of this lithium, then what we can say, the lithium can move around like free lithium. So therefore, both can be contributed to this screen. And this is the typical spectrum. You see the lithium D alpha reaction or DP reaction. Here, you see the DPT reactions here. And phase transition of lithium liquid metal is very easy to see. So this is the temperature versus time. Put a heater on, and then going up, the temperature goes up, and suddenly over here, it stopped for a while, but the heated up, of course. And then after that, it goes again. Here, the phase transition is occurring. And look at the yield of the DDPT reaction. You see, in this solid case, very high counting rate, but when it is melting, the solid target is start to melt, then it is going down. And in complete liquid phase, it's very small. That's because of the deuterium inside the metal cannot be stay, because no lattice structure. Just a lithium, post-metal lithium is just moving around. Therefore, no support to stay there. And then we measure the yield of a lithium plus D reaction. you see that this change. Liquid phase is always larger than the solid phase. Okay, this is the excitation function for that solid lithium case. And you can get this kind of screening potential for solid for about 400 electron volt. But when the liquid lithium case, the screening potential is much larger than, not much, but definitely larger than this change of this. And from these, we know the conduction for the solid liquid case, we have two electron contribution, conduction electrons, and also the binding electrons. It's bound to the lithium. And then we can get the conduction electrons for about 210 electrons. And for the ion case, another another screen potential contribute to this. And to fit these, we can get the U ion equals 420 electron. This is a little bit smaller than the opens, about 70%, 60 to 70% of Debye screening potential. And the temperature dependence in this Debye screening case, you know, the temperature, if temperature going up, then the screen potential is getting smaller. So we can see that effect. We change the temperature of a liquid lithium, then the delta US, that means difference between the liquid to atoms can be changed, can be lowered around this. This is the full case of a Debye model. So anyhow, in liquid lithium, temperature increases, but the screening potential decreases. And we can say this, lithium plus ions contribute to the screening also. That is maybe interpreted as a Debye-Hückel screening, but 60% of that. Okay, I guess I'm losing my time, so therefore I just I want to say that this one. I will skip this. Just say there is a very unique mechanism to using the molecular beam for the screen potential measurement. That's we call the cooperative colliding mechanism. If you use the molecular beams like the two here, one of the partner of the molecule first scattered by this host metal and scattered, and then meet the another partner and make a reaction here. So this is very advantageous to see to measure the screen potential, because there's no uncertainty about the number of target deuteron in the DD reaction. We know the target number of targets. And target deuteron is not fixed. So it is not affected by the effect of a lattice, etc. So therefore, the screening effect due to the conduction electrons only. And typical, how do we, How do we recognize this one has happened? This mechanism happened. This is the proton spectra, which is very much different, like this. And the normal case, I mean, deuterium inside the solid medium, indium case, it's very sharp. And then also the excitation function is very much different. For example, normal DD case, it goes down very fast. But in this case, it is slowly go down. And we can compare these to get the screening potential. But, and yeah, like this, but I just skip. But what I want to stress is, does this CCM affect the cross section for the solid metal experiment with a molecular beam? If you have this kind of, we always have this CCM process, even the target is solid metal. So therefore, we have this kind of, we know this intensity. And if you have a thick target yield by normal process, for example, deuteron density in the metal is something like this. You have this, your measurement is going down from, let's say, 25 bohm, and if using the deuterium molecular beam, then here you have an enhancement, even if there's no enhancement over here because of this effect. And then you might get the wrong, not true screening potential. For example, for this case, you can get the 500 electron volt screening potential, even if the screening potential is 0. Therefore, that's my just suggestion. When molecular beam is used, this process should be considered. Okay. Then we want to explore our question is it possible to provide high temperature and high rho region in condensed matter? So we try to liquid metal plus ultrasonic cavitation. The cavitation is something like that. If you have a liquid over here, then first some of the bubbles are here. Then it's a compressed, and then expand. It's the kind of ultrasonic cavitations going this way. And finally, it collapses. And then it collapse time, there might be the very high density region or high temperature region, because there's one group report that they used the deuterated acetone, and they said they saw the diffusion. This is the typical one when they observed the 2.4 MeV 2.4 MeV DD neutrons from DD reaction when this ultrasonic cavitation on. So we put the cavitation target like this. This can be provide a liquid lithium, let's say about a temperature about 210 MeV, and the ultrasonic is pushed from this side. And we have here very small region though. There is the cavitation. And This is a cavitation process, ultrasonic on and off, on, off, on. Yeah, if the ultrasonic cavitation off, there's very smooth surface over here. And ultrasonic on, here the very much cavitated surface over here. And comparison of on-off ratio for everything. For example, let's say this is a typical one. You see, this is the plot of this lithium 6 plus D alpha reaction case. There's no effect. This is the ratio of a yield ratio of ultrasonic on to ultrasonic off. By the way, this is a spectrum. You see that when the ultrasonic off on, you see the on case, the yield is very much enhanced, like this. In this case, this continues about 100 minutes. The ratio is almost 3.6, and sometimes more. Very much large contribution. Yeah, we observed the increase of yield of DT reaction, but no change in the yield of the lithium plus D reaction. The enhanced reaction lasts for 2 hours for maximum case. It stops due to the dirt of the surface. And we compare the proton spectra in detail. And we see the broadening of peak tails. Okay, so this is the DD-PT reaction proton spectra. In the US ultrasonic off case, we have, from off case, we got this line shape. And compared to the on case, and we got this black dashed curve is the same one as from here. So we really see the broadening of the spectra. And we can estimate how much temperature or the energy of the target in this case. I mean, deuterium inside the lithium 6. And then we estimate that the temperature is about, energy is about 700 electron volt. That means temperature is something like 10 to the 6. By the way, in the lithium case, there's no change. So no effect of ultrasonic for the lithium plus D reaction. But for the lithium DD reaction, we got a real effect. And just to see that this on-off ratio, average value though, plot as a function of a deuteron energy. And then again, to fit that. And from here, we get this thermal energy, about 600 electrons. It's consistent with an analysis of a proton spectrum. So therefore, our liquid metal, once got a ultrasonic cavitation, this region is going up to this part. It's very high temperature, and the density is like similar to this. That's a very nice thing. Okay, just summarize this. Screen potential for D plus D and the lithium plus D in various conditions. Okay, we have a atomic or molecular. This is just a bound electron, screening from bound electron, and typically around 25 electron volt. And for the lithium plus D or lithium plus reactions, around 300 electron. By the way, these are some kind of prediction. It's always larger than that. And in metals, only the conduction electrons, the many metals are something like this one. And as I told you, this is always larger than that. And for the lithium plus D reactions, we did one experiment in palladium case, and it gets a very large screen potential for the palladium case. And in the solid lithium case, we have something around the 400 electron volt screen potential. And the lithium, in liquid lithium case, also the very large screen potential. And as we said, as I showed, the liquid lithium ultrasonic cavitation, we can realize the high temperature plasma, something like the temperature, something like this. That corresponds almost, if we said the screen potential, then there's more than 2 keV. So, but is it possible to DD fusion to as a energy source? We know the DD fusion in liquid lithium cavitation, and we can compare these conditions as, for example, ITER project condition. And I would say, as far as rho square sigma is compared, the cavitation has a 10 to the 4th times advantage. However, practical energy production is difficult to high density if high density can only be achieved within 10 picoseconds. You see the cavitation, ultrasonic cavitation is very sharp stage. So much higher T and rho are desired. It's still we have to develop. For example, on the other way, the diffusion in conduction electrons in metals, and the rho is this, and let's say temperature is like this. And for example, we can get the sigma cross section, something like this, or if we have a electron screening potential, 300 electrons. And then we got a 10 nanowatt per cubic centimeters. And also if we got this kind of large cross-section, if we have a very large screen potential, then we could this. But however, is this connected with a fusion, cold fusion? And we will discuss just below. So we started the generation of thermal energy for exciting chemical reactions. Our method is like this. This is the sample. Sample is the foil of nickels on nickel substrate. Let's put 2 sample foil, A and B, put the heater over here. It is ceramic heater. And before the measurement, these things are evacuated. The hydrogen is introduced to have a hydrogen, the sample hydrogen. And then it's evacuated. Yeah, first sample filled with the hydrogen gas. And to get excess heating and evacuating. Temperatures up to 100 K, pressure is going to 10 to the minus 50. And heat flow, this is almost an isolated system. Heat flow carried out almost by radiation photons. So therefore, we can measure the radiation from here. Then we can know how much energy produced in this very small system. So this is the measurement procedure. First, we do the background measurement before introducing the hydrogen or deuterium gas. That is, without hydrogen, we heat up and then measure the radiation spectra at various heat voltage. And then the excess heat measurement cycle follow this one. First, absorption of hydrogen or deuterium. Hydrogen pressure is something like this, and the temperature is something like that. And we stay this one for, let's say, about 15 hours. Then in the morning, evacuate the chamber, set a heater for a measurement, and then it heat up. During the desorption, radiation, we measure the radiation and to see. So, okay, this is the just the photon detectors. We use the 3 photon detectors. One is mid-infrared region and the near-infrared region and the optical region. So these are the things. And put the sample over here. Both radiation are measured like this way. This is the typical radiation spectrum. Mid-infrared region, this is just covered, not a spectrum, but just covered average intensity. So you can see that this black dot is the radiation intensity without hydrogen. It's in vacuum condition. So this is the background. And hydrogen desorption case and the deuterium desorption case, you see the increase of the intensity from here and here. So what is this line? Oh, this is just a gray body radiation presented by this formula. And we need just two parameters. One parameter is emissivity of the surface, and the other one is the surface temperature. So by this fit, we can deduce the emissivity and the temperature. And during gas desorption, of course, the temperature is increasing, and also, but the emissivity is decreasing. However, as you see, obviously the radiation power, all power, is obviously increased. In this case, about 7% or so. And the other thing I would say, no difference between the hydrogen gas and deuterium gas. Okay, this is the evaluation of this power. I just skip it, and this is the calibration curve for this evaluation. This also skip it. So, so I just put the result over here. Also, this is the excess heat. That's a watt for from the sample. You see, if there's the no sample, no hydrogen case, you see the fluctuation is this is just a so-called systematic error of this measurement. And these are the random errors of this measurement. In nickel copper case, it's very much higher than this one. Let's say the 5 watt. And the nickel alone case, very small. So what I want to say, nickel substrate alone seems to produce very small, very slight excess heat, excess power. And also the monolayer copper slightly produces excess power. And also, I would say, the complex nickel copper case certainly produces the excess power. And amount of excess power similar for hydrogen and deuterium. And this is the measurement for the long-time behavior of excess power. For this case, the deuterium absorption, and for this case, hydrogen absorption. So this is continued for very long time, around 4 hours, and for the hydrogen case, just a little bit small, larger than that for that. So we would say the excess power does not decrease even after 80 hours because we don't know, and is almost constant on over average over time, although it is accompanied by large short-term fluctuation as if oscillating. And also no significant difference in excess power between hydrogen and the deuterium under similar condition. And we estimate that how much energy produced by using the small amount of initial hydrogen gas. And in this case, the initial absorbed hydrogen is very small, only 6 times 10 to minus 6 mole. And the produced energy in this region, we got a 520 kilojoule. And then we calculate this using, this is exhausted by some kind of reaction for making this excess power. Then we got this excess energy production per hydrogen. This is the minimum case because we don't know how much exact amount of hydrogen is exhausted by the reaction itself. So we said this is more than 460 keV. It's very large. All right. So the thermal energy for hydrogen, let's say we estimated from simple multi-proton reactions. Only this case can be the candidate because this is the 4p case, 4p plus electron over here. But in this case, we always need a weak interaction. The initial stage electron should convert it to the neutrino. And then the neutrino get almost many part of energy. So therefore, the energy for the heat is very small, even if this Q value. And we estimate that this one for the proton emission and helium-3 emission, and energy loses inside the sample, only the 200 keV per proton is left for the thermal energy. You see, we have observed thermal energy for hydrogen is larger than 410 keV. And if we have a thermal energy from the similar process for deuterium to 2-alpha reaction, then alpha loses his energy inside the metal sample, then the energy produced per deuterium is 11.9 MeV. But we have this observation. So therefore, I would say the elementary reaction of energy production is still mysterious. So let me summarize. In the first half, we learned metals provide laboratory plasma with low temperature and medium density. We see the solid DD reaction in solid metals and liquid metals, and also liquid plus ultrasonic cavitation. And then we know that electron screen, much larger than Thomas Fering screen. In this point, the Chelsky proposed there might be the narrow zero threshold state, which I think will be discussed more detail by himself. And we saw the ionic screening effect that is smaller than device screening by amount of 60%. And liquid lithium metal with ultrasonic cavitation makes very high temperature plasma. In the second half, the nickel copper multilayer foil with hydrogen gas or deuterium gas produce thermal power, excess power of about 2 to 6 watts. This is very large. And then we calculate the produced energy of hydrogen in the foil is much more than 400 keV. This is much larger than, of course, chemical reaction. However, it is difficult to connect the thermal energy generation in the metal foil with the fusion reaction in the plasma. For example, the thermal power generated is almost the same for both H2 and deuterium gas. Okay, this is a near future project, the experiment which we are thinking of, search for non-thermal photons. This should be, this is to find a path to the thermalization from the very high density production. We have this region already, and we measure these region, gamma ray region, and also the X-ray production, but no excess yield, no Bremsstrahlung, no characteristic X-ray and gamma rays. We didn't find any connection between the between thermalization and the large energy production. Here we didn't know that. Maybe next year we will put this one here, and also the from the very near future we'll put this one here. So this is the our future project. Okay. All right. This is my talk. Okay. Thank you very much for listening to my talk. Thank you.